Okay, we're going to today finish up this example, which will finish up these slides. But I said something really stupid last time. I know what you're thinking. Mr. Miller, you say something stupid. No. Okay. I said there was a test on Monday. There may be a test on Monday, but not in here because we are on break on Monday. All right. So it's going to be a test the next Monday. Right. I do not like tests as soon as people get back from break. Okay. I don't like that. But I know that if I put it on Wednesday when you get back from break, people won't even touch it until after break. And if you go 2 or 3 weeks without looking at this stuff, that is the best. If I had to write a prescription for a class to do poorly on an exam, that would be it. Have a difficult chapter, or let's just say the first college level chapter. The first college level chapter, where half the class is behind, and then give them 2 or 3 weeks before the tests. If I had to write a prescription on how to make a class fail a test, it would be that. Right? But I know better than to put it on Friday. Right? Friday before break, there's, you know what it is, spring break flu. Oh, Mr. I can't make it. It's terrible. Oh my God. I could be in quarantine for 6 months. Right. So the exam flu is terrible before break. Oh, it's epidemic. It's epidemic. So anyway, the money we get back, and that is going to be March 15th. March 15th. Is that Ides of March or something? I think it is. All right. Now, so I'm going to finish this example here. Talk a little bit about the test. Did last time. I have right now slides for chapter 4 being printed out downstairs. Run down to get them, and we're going to start chapter 4 today. We're going to do chapter 4 on Friday. All right. So chapter 4 today, chapter 4 on Friday. Chapter 4 is more of it's very different than chapter 3. Chapter 4 is it's exponential logarithmic functions, but it's material that most students have not had before, so you don't have as good of a basis in it, and it requires you more to keep up, right? So last time we had begun this example. Don't forget the secret first step or secret 0th step, right? If these coefficients are all divisible by a number bigger than 1, you factor that number up front. They all have to be divisible by that number. They all have to be divisible by that number. If you're going to apply the rational 0 theorem, which you are, if you're going to apply that, all of these have to be integers. So if you factor something off and creates a fraction, the rational 0 theorem no longer applies. All right? No longer applies. Okay? So what do we have? We did the rational 0 theorem. We got this list of candidates. Right? We start trying the candidates. We tried 2, and it worked. By work means it had a remainder of 0. The most important slide of the chapter said that if this is a root, if that's a root, then x minus that number is a factor. A root makes the function 0. So if you'd have taken that 2, plugged it in here, raised it to the 5th power, which is like, what is it, 32 or something, minus 2 times that to the 4th power, minus that cubed, you'd have done all that, you would get 0 if you do it correctly. Right? This is actually easier because there is almost nobody that's going to do that and not make an arithmetic mistake at least the first time through. Right? So this 2 becomes it's a root. X minus 2 becomes a factor. The most important slide of the chapter had a concept on there that you can then factor the original function. You can factor that x minus 2 off. You can take that factor it up front. You're left with a polynomial of 1 lower degree. Our original polynomial was degree 5. That's degree 4. And you get those coefficients. Those green coefficients are these numbers right here. These are those green coefficients right here. They go over to here, into here, into there, right? Oh, into there. That's where those coefficients come from. So then we tried, well, 2 worked one time. After you do this, you always do the rational zero theorem again, and you see that you have a list of candidates. Notice that 8 is no longer on the list. And that's what you want to do, is you want to narrow down that list. So a list of candidates, 2 is still on the list. 2 worked once. It could, in theory, work again. It turned out that it didn't. It gives you a remainder of 16, which is not, means it's not a root. Oh, so I'm going to write that out here. This means x equals 2 is not a root of this. It was a root of our original function, but it's not a root of this. This is what we're trying to factor now. We took off x minus 2, which accounts for it being a root of that one above. Now we're trying to factor this, and x equals 2 is no longer a root of what's left. So we throw it out for the rest of the problem. All right? Then we bring these coefficients down here and try again. The same coefficients we bring down. Don't make a copying error. The most common error to make between here and here is to drop a negative sign. So one of these negative signs would get dropped. Okay? So we try minus 2. We do the synthetic division, and it turned out to work. So this means by the way, you notice I've been writing means a lot on the board. The reason why is that you need to know how to interpret the various steps, not just memorize them. If you're memorizing them, you're cramming them. And cramming doesn't get you very far, and this is conceptual, right? I could get into brain mapping and how your brain maps this kind of learning versus memorization. I could get into that. It would go in most people one ear and out the other, right? Right. So I'm not going to, but I will say memorization only gets you so far. There are things to be remembered, but memorization cannot be your primary learning strategy here. So this means, I'm trying to interpret it. That means that this is a root. It means x equal 2, minus 2, excuse me, is a root. That means x minus 2, you subtract the root, x minus 2, which is, of course, x plus 2, is a factor. So, the most important slide of the chapter, you can take that factor and factor it up front. So now we can write our function, no longer writing our function like that. We can write our function f of x equals the x minus 2 from last time. And then this time we picked up an x plus 2 factor times a polynomial of 1 lower degree. So there's another polynomial going to go here. It's going to have 1 lower degree. This had degree 4. This is going to be degree 3. So you're going to have something x cubed plus something x squared plus something x plus a constant. That's what degree 3 means. Those coefficients are these. Those coefficients are these. So we're going to put there 1 minus 2 plus 3 minus 2. Okay. What do we do now? We do the rational zero theorem again on this. Notice that, well, here, we'll see. Factors of your, using the rational zero theorem, factors of -2 are plus or minus 2, plus or minus 1, divided by factors of the leading coefficient, which is plus or minus 1. That equals plus or minus 2, plus or minus 1. So our list of candidates went from 6 down to 4. It's getting smaller each time. Right? Now, this is another ninja trick. We did a ninja trick last time. If these come out to be all, it might have been last time or time before. If all of these come out positive, you can throw away all positive roots on your list. If all of these come out positive, you can discard all the positive roots on your candidate list because no positive root will work. That was the little ninja trick from last time. A ninja trick from this time is the fact that there's a 2 right there, tells you one of these 2's have to work, plus 2 or minus 2. Let me say that again. The fact that we have a 2 for a constant term tells you that one of these 2's is going to work, either plus 2 or minus 2. Now, which one's going to work? Minus 2. Plus 2 cannot work. Why can't plus 2 work? Because we tried it up here. It worked once, but it did not work again. So once you try a root and it doesn't work, you abandon it for the rest of the problem. So we abandoned 2 up here. So I can ignore positive 2 in this list. And I know, because of this green 2, I know that minus 2 is going to work. So I predict if we try minus 2 again, it will work. We'll put a minus 2 out here. And I say we're going to get a big fat Greek 0 right here. That's what I say, okay? We'll see what happens. 1 minus 2 times 1 is minus 2. That is minus 4. Ain't working. That is funny. That 2, you know what? I caught myself. That 2 is going to be part of our complex solutions. Okay? But anyway, we still learned something here, okay? Minus 2, that's a 4. That's going to be an 8. That's going to be 11. 2 minus 22. That's not going to be a 0. That's going to be a minus 24. That is not 0. I caught myself on something. You're going to see where this 2 comes in a second. You're going to see where it comes in a second. So what happens? That means this is not a factor of this, contrary to what your instructor said 2 minutes ago. So this is going to be x equals minus 2. This means x equal minus 2 is not a factor of this. Now, it was a factor up here, but it's not a factor of what we have left. So we know plus 2 is gone. We know minus 2 is gone. So we got either plus, we're going to use these same coefficients again down here. We're going to write the same coefficients again, and we're going to try it again. We have 1 minus 2, 3 minus 2. So now, only thing that's left is plus or minus 1. Plus or minus 1. I'm going to pick one of those because we know the 2's are gone as far as being rational roots. We're going to see that there's a 2 is going to come up here in a second. a different way. Yeah, you said that last time, Miller. So that's going to be a 1. Put a 1 there. Bring a 1 down. 1 times 1, 1. Add minus 1. 1 times minus 1 is minus 1. Add, you get 2. 1 times 2 is 2. And there is our missing 0. Okay. What does that mean? This means x equals 1 is a root. That means that x minus the root, x minus 1 is a factor. Right? X minus 1 is a factor. Right? What does that mean? I can factor it up front. I can factor it all up front. So this f of x, we write this again, f of x, x minus 2, x plus 2 from our previous steps. Now this step, the new factor is going to be x minus 1. X minus 1. And then what we have left is a polynomial of 1 lower degree. Polynomial of 1 lower degree. X minus 1 right here. These are the coefficients. So you're going to have x squared, something with x, and a constant. What are the coefficients? These. 1, minus 1, and 2. Okay. Now, if I did rational zero theorem again on this, what would I get? I'm going to get this same thing as up here. Plus or minus 2, plus or minus 1, divided by plus or minus 1. That's going to be plus or minus 2, plus or minus 1. Okay. I say now, none of those will work. Could I try more? I could try more. For example, if you went right here and you tried again, 1 worked. So if you tried 1 again, 1. 1 times 1 is 1. 0. 1 times 0 is 1. 3. And that is not equal to 0. Right? So 1 is not a root. If you tried minus 1, it would not be a root. Why do I know that? Because look at that quadratic. How do you know if a quadratic has real numbered roots? We had a quick little test in chapter 1. How do you know whether a quadratic, how do you know how many real roots a quadratic has? Crickets. The discriminant. I think some of you knew. Just doing the same. It's called the discriminant. So on this, you're going to apply b squared minus 4ac. Remember the essential skill? Remember what I said we were going to use later in this semester? B squared minus 4ac. These green coefficients are your a, b, and c. So b squared is minus 1 squared minus 4 times a times c this is 1 minus 8. That equals minus 7, which you will observe is less than 0. What does that mean? If something has a negative discriminant, it does not have any real roots, a quadratic. It does not have any real roots. Okay? So that means no real roots. So if it has no real roots, it's not gonna, none of these are gonna work. Because those are real numbers. If it had any real roots, those could work. But since it has a negative discriminant, none of the remaining candidates are gonna work. So what do? You plug it into the quadratic equation. So the fact that it doesn't have any real roots does not mean that it doesn't have any roots. It means it doesn't have any roots on the number line. If you were to graph this as an equation, excuse me, a function, that would be a parabola opening upward. That would be above the x-axis. It would not touch the x-axis at all if you turn that into a function. So it has complex roots. So what do you do when this happens? And by the way, Mika Ray, who was doing the review problems at the end, the review problem at the end is that way. This is what we were talking about the other night, right? And props to you, girl, for working ahead. You put it in the quadratic equation. X equals minus b. So minus the b is a positive 1. Plus or minus the square root of b squared minus 4ac. That's this. It's going to be minus 1 squared minus 4 times a, 1 times c, 2. Divided by 2 times a. That's 2. This is going to be, we already know this comes to minus 7, right? So that's going to be 1 plus or minus square root minus 7 over 2. Don't leave it like that. Because you got to turn those into roots. And you got to simplify it. You can't leave it like that. That minus 7 has a perfect square embedded in it. You know that you can take a perfect square outside the square root sign. You can take a perfect square outside of the square root sign. So what you need to see here is this. 1 plus or minus the square root 7, minus 7, excuse me, is minus 1 times 7 over 2. Minus 1 in this class is a perfect square. So this equals 1 plus or minus square root 1 minus 1, excuse me, is I squared. Minus 1 is I squared times 7 divided by 2. And so that I can come outside of the radical. Because you have an I squared under the radical. That can become an I outside the radical. Right? This equals, we can split this up. 1 over 2 plus or minus square root of 7 over 2 all times I. Oops, I. Wrong color. Okay. Just as a convention, we put our i's after the coefficient. I don't care if you put the I before, as long as it's outside the square root. But the convention is you put the I outside afterward. So those are 2 complex numbers. So let's pause here for a second. Complex numbers are, they exist in the universe just like the number 3. They're not, I mean, they're a little bit mysterious, and sometimes they're called imaginary numbers, right? But complex numbers exist in the real world as much as any other number on the number line. It's just that they're not on the number line. And I've mentioned before, but your world would be very, very different without complex numbers. For one thing, you wouldn't have these. Nothing that involves a silicon chip would exist without complex numbers, right? Computers would not exist. The internet would not exist, right? How different would our world be without complex numbers? Now, there and some other stuff, okay? But without complex numbers, you don't get the mathematics necessary for electromagnetism and what you need to do processors and stuff like that, right? So get used to these being possible solutions. So what do you do with them now that you have a solution? This is where that 2 went, by the way. The 2 I thought was going to be a root over here. Wound up with egg all down the front of my shirt. Wound up with egg on top of my belly. Had to brush it off my belly. You do the same thing you do with any other root. What did you do when you got a root of 1? What did you do with it? That meant that x minus 1 was a factor, and you made 1 a factor of x minus 1. We're going to do the same thing. We're going to make those factors of x minus each one of those. So, ergo, we're done, by the way. We just have to write out our answer. And this is the way you need to write out your answers. This is the way the answers are in the book. This is the way the answers are in the solutions at the end of the slides here. Our f of x, our original function, factors as follows. These factors here, x minus 2, x plus 2, x minus 1. In fact, we're going to have to go a little further down. I'm going to have to clear out some space here. Sorry, guys. I just rearrange the furniture there a little bit, so I don't have to go as far down here. So these factors were all from up there. Those were all real factors. Now we're going to add the complex factors. How do you do that? X minus the root. X minus, there are 2 roots there. One root is 1/2 plus square root of 7 over 2i x minus 1/2 minus, I'm going to put it in bold, minus the square root of 7 over 2i. You see how to write those complex factors. It's the same as these, really. It's x minus the root. Now, by the way, you do need this extra set of parentheses, or you're going to need to flip the signs inside. You're going to need to flip those signs. One of the two, all right? So this is our answer. That's our answer. I'm going to go back and do some talking. I want to know if there are any questions. Any questions now? All right. Then I'm going to go downstairs and get the get the new slides off the printer real quick. So we picked up around halfway today, and what we kept doing was we kept working our list of the rational zero theorem. We worked it until the list didn't work anymore. If your list doesn't work anymore, you're either doing something wrong and you made a onesie-twosie mistake up above, which I have done many times. If you do a onesie-twosie mistake here, you may get something, have a zero remainder that isn't a root. And that sends you off into very arid country. Okay. The second thing is you did it until we got down here, and this had no real roots. None of these worked. So if there are no real roots, that means you have complex roots. You have complex roots. Okay? And we apply the quadratic formula. You know how to do the quadratic formula, right? It was on the last test. How did you do on the last test? I gave you the formula on the last test. I can promise you, you will not have the formula on this test. I'll promise you. If you need that, you know how to do it. So the quadratic formula is not too much to ask in the college algebra class. So you do this right here, you wind up with two roots. How do you write the final answer? It told you to factor. It didn't say find the roots of. It says factor. So your final answer is going to be the factorization. But you do it the same way you did any other root. You did x minus one complex root, x minus the other complex root. All right? I am going to now, I think I'm done with that anyway. So here, here's some review problems. There's a problem right there. Oh, by the way, that looks like the secret zeroth step can work there, right? Shouldn't tell you that, but all those are even. If they're all even or all divisible by 3, factor that up front. It will save you some work, okay? All right. Let me run down real quick and get the slides off the print. We're going to start chapter 4. Chapter 4 starts with some fairly basic stuff that should be stuff you've seen before. But exponential and logarithmic functions, they should have been in a good Algebra 2 class, but I can in most cases, people are rusty in them. One key aspect going into this: exponential and logarithmic functions are in a relationship. They are in a relationship. What relationship are they in? They are inverse functions. Inverse functions. Inverse functions undo, one undoes what the other one did. All right, we'll get into that. So first we need the concept of a composite function. A composite function is a function of a function. What does that mean? That means you're taking the result of one function and plugging it into another function. Let me give just a crude example. Most of you had to complete your FAFSA, right? Some of you needed the finance office to call you 19 times to fill out your FAFSA, maybe. I don't know. I know some people don't get the idea that without the FAFSA, you're not in college. Without the FAFSA, you don't get financial aid. That's not your college's rule. That's the federal government's rule. You can thank the federal government for that, right? But the FAFSA does what? You basically unzip your life, show them all your finances, show them all your parents' finances, and it comes out with something called the EFC, right? The expected family contribution. Ostensibly, the more needy somebody is, the lower the expected family contribution. That's generally how it works. Unfortunately, if you saved any money yourself in high school, you got penalized. You got penalized. If you worked hard and you put your money away for college, you get penalized in how much financial aid you'll get, because you're considered richer. Okay? That's the facts. If you spend it all on cars, girls, and pizza, you get more money from financial aid. Yeah. That's a good lesson. So you get your expected family contribution. How is that used? That gets put into another formula for your scholarships, right? How much scholarship money you're eligible for. Okay. So you take the output of one function and it goes into another function. It goes into another function. And then that gives a number for your scholarships, and also you subtract those two numbers from the how much you owe, you get the how much you're going to have to pay out of pocket for college, right? That's how that works. So you're taking the output of one function and putting it into another function. That is called a composite function. Composite function, right? So that works like this little drawing down here. Suppose you have a function g. Suppose g is the FAFSA. It takes your data in FAFSA and spits out a number g of x. This number is your expected family contribution. That gets plugged into another formula at different colleges, and that results in f of g of x. It took the output of g, it went into a function f, and gave you a number of what your scholarships would be. Some scholarships are need-based, some are merit-based, right? Right? Some are because you're an athlete, regardless of how needy or whatever your financial situation of your family is, right? That's how that works. Others are need-based, right? Based on somebody's financial need, okay? So it's a function of a function. So this is another little drawing of it where we have, you can picture a function as this little machine. Up here is the function g. It's a little machine. X's go in. Some other number comes out that we call g of x. G of x is just another number. So a function is a machine that squares inside the machine. The number gets squared. It gets 5 subtracted from it. You divide by 17. You take all that to the third power or something, okay? It crunches the number. And it spits out a different number, g of x. G of x then gets plugged into a second function. So this is your EFC, or excuse me, your FAFSA. It spits out a number called your EFC. Your EFC goes into this box here. That crunches it again, right? The college will look at that. It goes through their scholarship machine, and it spits out, here's how much scholarship you're getting. Right? That's how that works. Okay. Now, this machine may add money due to your merit scholarships, right, or stuff like that. And then there's going to be need-based component. It gets you a number of scholarships. You subtract that from what you owe of the total number, and that is your how much you're going to owe. Right. The composite function would take this original x and take it all the way down here. The composite function gets you there in one step. Instead of plugging into two functions, you plug into one that does the whole thing. That's the composite function. Right? Here's some examples of composite functions. You're plugging one function into another. Now, there's this strange notation that was back here. This notation, notice this stuff here. That looks like fog. That is read f of g of x. F of g of x. And this is what it means. This means you're plugging g into f. So down here, for that being f and that being g, what is f of g of x? This means you plug g of x into f of x. G of x into f of x. Well, what is g of x? 1 minus x. What does that mean? That means you're going to look at the function f. You will look at the function f, and everywhere in f that there's an x, you're going to replace it with 1 minus x. So I go up here to f, that's 2x squared. Instead of that x, I'm going to put 1 minus x. So that's going to be 2 times, instead of x squared, it's going to be 1 minus x squared. So right there is f of g of x. This is our answer. This function would take an x directly to the number at which it would arrive if you plugged it into one function, took the result, and plugged it into the other. Now, what if you do it the other way around? Any questions on what we just did? What if you do it if you did this the other way around? I'm going to go here. 1 second. G of f of x is you're going to take g of x and you're going to plug in f of x into g of x, the other way around. G of f of x is the same as g of what f of x equals. F of x is 2x squared. What does that mean? Again, interpreting. We're trying to interpret each of these steps. What does this mean? This means everywhere there's an x in g, I'm going to replace it with 2x squared. So g is 1 minus x. So I'm going to write this as 1 minus what I'm plugging in for x, which is 2x squared. Right? Right. Okay. Questions on that? You're plugging one function into another. When we say plug in, we mean everywhere an x appears in the other function, you're putting a function in instead of just a number. There's some love for next time. Right? Now, inverse functions. Inverse functions undo what the other function did. So you're asked to complete what is f of g of x for these two functions. What is f of g of x for those two functions? So f of g of x, that equals, that is f of g of x So I'm going to look at my f function right here, and everywhere there's an x in it, I'm going to put g. Everywhere there's an x in it, I'm going to put g. So this is 5x minus 3. But instead of x, I'm going to put what g is. That is 5 plus 3x divided by x. I'm plugging g of x in as if it were a number x. What does that give me? Ooh, I got to simplify that. How do you simplify that? You simplify that by clearing some fractions. At the start, I have an x in the denominator here. It'd be nice if I could multiply that entire denominator by x. But if I do it on the bottom, I got to do it on the top. Right? So notice I'm going to be multiplying by x over x, which is 1. X over x is 1, so it doesn't change the value. It just rearranges the furniture. So in the numerator, I have 5x. In the denominator, I need to distribute this green x across two terms. The green x times the red stuff, and the green x times minus 3. The green x times the red stuff cancels the bottom red x. That's why we picked it. So x times the first term just gives me 5 plus 3x. The x on the bottom cancels. Minus 3 times x. There's our green x right there. All right? So what happens? Well, lo and behold, those cancel. This equals 5x divided by 5, which equals x. So f of g of x in this case, you stick an x in, you get the same x out. Got 1 minute left. This g of x does something to a number, and we're going to demonstrate this down here on Friday. Okay? Actually, on the next slide, right? On Friday. This g of x does something to a number. It sends x to who knows where. F of x undoes everything g does and gives you your original x back. So this means that f of x and g of x are inverse functions. All right, we'll leave it there. Test the Monday when you get back. That is the 15th. My advice is do not go into break behind, because you know you're not going to look at much of this over break. Every break, I used to take home a big stack of stuff to grade and stuff to prep and slides to do. I never did any of it. I shut my office door now and I go enjoy my break, but I bust my tail beforehand and have a great break. All right. So see you guys.